on your own, but I'm not assigning anything from there. Okay, so what we want to start today is section 1.8, and this section is on what we call continuity. And so I'm going to start with the definition of this term. We say that f, let's say f is a function. F is continuous. F is continuous at some number a if number 1, f of a is defined, it means that a must be in the domain of f, and 2, the limit at a is the same as the value of the function at a. We have seen many examples of functions where the function is undefined at a point, but the limit exists, right? We also saw that a function may be defined at a point, but the limit may not exist at that point, right? For example, we saw so recall that we saw this graph of a function that looks like this, and let's say I have the number 2 right here, okay, and whoops, so if I look at the function x squared minus 4 divided by x minus 2, right, this function, the graph of this function is this straight line with the hole at 2, right? Because you can factor out x squared minus 4 as x minus 2x plus 2, and then this function is in fact the same as x plus 2, except at 2. So for this function, notice that f of 2 is undefined, right? F of p is undefined, but the limit exists, right? So this is going to be, this is not continuous at 2, right? Because continuity at 2 would mean that the limit at 2 is the same as f of 2. Okay? So the limit here, the limit at 2 for this function, okay, is equal to 4, which is not the same, and let me call this function f of x, okay, which is not the same as f of 2. Even if f is defined at 2, maybe the function is defined by this value, okay, f of 2, let's say f of 2 is the value, if this is 4, then 2, let's say this is let's say that height, you know what, let me just pick another height here. Let me pick this height, and that would be 8, let's say. So let's say f of 2 is 8. In that case, the value of the limit is not the same as the value of f of 2, even if f of t is defined, right? Okay, and we also saw another possibility, which is we might have a Maybe I have the graph still somewhere here. Well, I can't find it now. But the example that I have in mind is the following. So let's say I have a function which looks like the following. Okay, so let's say I have a function which is some function f of x. I'm not telling you what that is, but the graph of this function looks like this. Then what is happening, let's say this number here is 1. Notice that the limit at 1 does not exist, right? If the f of 1 is defined, there is a value of f at 1. However, the function is, there is no limit at 1, right? Am I making sense? So this function is not continuous at 1. So again, going back to the definition of continuity, it says that f is continuous at a number means that f of a must be defined and the limit at a must be the same as the value of f at a. Okay, so the first example, I wanted to make the point that sometimes the limit may exist, but the function may not be defined at that number, or maybe even if the function is defined at that number, the limit may not be the same as the value of the function at that number. And then in the second example, we see that the limit doesn't exist, right? The limit doesn't exist. So there might be the case that the limit doesn't exist even though the function is defined at that number. So if we say that f is discontinuous at a if it is not continuous at a. I'm going to write CTS for continuous, okay? And for discontinuous, I'm going to write DIS CTS, okay? Sometimes people will say we also say f has a continuity at a. Okay, if f is discontinuous at a, then we also say that f has a discontinuity at a. Another thing that I want to write is that let I be an interval f is continuous on I. When we say that f is continuous on I, what we mean is that f is continuous at every number a inside of I, okay? So when we say that f is continuous on an interval I, it means that f is continuous at every single point in that interval, okay? So at every single point in the interval, the limit of the function and the value of the function are the same, okay, at every point. And pretty soon we will see that what it means for a function to be continuous on an interval is that the graph of the function, you can trace the graph of the function from one side to the other without lifting your pencil, okay? So we'll see that in a bit. So I want to go over a couple of examples now. Yeah.
What's the A sigma I?
What is what?
What's the A stand for again?
Oh, A, then this is like epsilon. This means A is inside of I.
Oh, okay.
Yeah, A is, so every single A in I. Okay. Example. Let's say I have the function f of x, and f of x is a polynomial x squared minus x. Okay? And I want to know, I want to determine all the values of x where this function is continuous. Okay? Find all values of x where f is continuous. Find or determine all values of f where f is continuous. Well, let's see. Let's say let's let A be any real number. Okay, so A is any real number. Then let's see what's the. Then we know that this is a polynomial, right? So the first condition of continuity is satisfied, right? F of A is defined, right? Number one, F of A is equal to A squared minus A. So that is defined, right? That is defined because it's a polynomial, right? Given any real number, I can square it. I can subtract A from the square. And number two, I have to make sure that the limit at A is the same as the value of f at A. So what's the limit at A of x squared minus x? Well, if I have a polynomial function, we know that we can find the limit by what? By plugging in the number, and in this case we see that the value is exactly f of A, right? So the limit at A is the same as the value of the function at A, okay? So both conditions are satisfied for any given point A, right? So in this case we say that f is continuous on the entire set of real numbers. Okay? What do you think the answer would be if I give you another polynomial? If I give you another polynomial and I ask you to determine where the function is continuous, what do you think the answer is? All real numbers. Okay, so this works for every polynomial. So generally, for any given polynomial function, it is continuous everywhere. Okay, so you have to remember that. So here's the remark. If p of x is any polynomial, then it is continuous everywhere. I.e. on negative infinity to positive infinity. Okay? Yeah.
So are we just basically finding the domain of the limit?
Are we just finding the domain? Yeah. I mean, most of the most of the kinds of functions that we look at, they are continuous on their domain. Okay, well, I'll make a remark in a few minutes. Okay. Okay, so just a few minutes ago, I gave you one example where we saw this example here. In this example, the function has a limit at 2, but that limit is not equal to the value of the function at 2. And in the second case, we have that the function is defined at 1, however, the limit at 1 does not exist, right? Because the right-hand side limit and the left-hand side limit are different, right? So, so this is not... Now, when I have a situation like this guy here, in this case, notice that if I look at the right-hand limit, of the function at 1, it exists, right? And it is equal to the value of the function at 1, right? So in this case, we say that this function is continuous from the right at 1. However, how about left? Can I say that it's continuous from the left? No. The limit at 1 from the left exists, right? However, it's not equal to the value of the function at 1, right? So it's not continuous from the left, it's continuous from the right. Is everybody okay with that? All right. Let's look at another example. Oh, by the way, in the second example that I have, the discontinuity that I have is called a jump discontinuity. So at a point, you have a jump discontinuity. When I say that, what I mean is that the right-hand limit exists, the left-hand limit exists, but they are different. Yeah.
So, say the point -1.
Yeah.
Is that continuous? Is this continuous from both the right and left hand?
Yes. The limit. This is continuous at 1.
Okay.
Because the limit at limit at -1 is the same as the value of the function at -1. So this is continuous at -1. This is called a jump. So at a point, whenever you have a discontinuity, it's called a jump discontinuity. If the right-hand limit exists, the left-hand limit exists, but they are different. Okay? Then it's called a jump discontinuity. But sometimes you might have infinite discontinuity. That is, you have a vertical asymptote, right? So we have seen many examples of vertical asymptotes before. Let me see if I can pull out one of them. By the way, if I look at this graph here, is this function continuous everywhere? It is continuous everywhere. Okay. I am trying to find out one of the examples that we did where we had vertical asymptotes. Oops. Let's look at this example here. The blue curves, right? The blue curves, if I look at them, that's the graph of x over x plus 1. And notice that at -1, so the blue curve is x over x plus 1. And notice that at -1, I have a vertical asymptote. The function is undefined at -1, right? So right away, you know that it's discontinuous at -1. Same way, the red curve, I think the red curve was what? What was the red curve? X plus 1 over x. And this guy has a discontinuity at 0, right? This guy has a discontinuity at 0. And it has a vertical asymptote there. Is everybody okay with that? Any questions? Okay. Now, in one of the examples today that I did, one thing you want to notice here is that in my first example, this function is discontinuous at 2. However, notice that I can redefine the function at 2 in such a way that I can make this function continuous at 2, right? That is, if I just change the definition of the function at 2 by saying f of 2 is 4, right away then this hole will be filled and then this becomes continuous, right? This is called the removable discontinuity. Removable discontinuity at 2. Meaning that you can redefine the function at 2 in such a way that you can make the function continuous at 2. But in my second example, the discontinuity that I have, this is not a removable. Because no matter how you redefine the function at 1, right? Do you want to redefine the function at 1 to be this value, this value, this value, this value? No matter how you redefine the function at 1, it cannot become continuous, right? You guys see that? This is not going to be a removable discontinuity. So in the homework, if you see the word removable discontinuity, it means that you can redefine the function at 2 in such a way that it becomes continuous. Okay. If you have a jump discontinuity, there is no way you can make it continuous at that point. Okay. So and you can make a function continuous only if there is just a hole, right? You just fill in that hole and then it becomes continuous. Okay. Any questions, anybody so far? You guys remember this function from before, I hope. Let's say I have the function g of x, which is x squared times sine of 1 over x. Can you tell me where this function is discontinuous? Where is this function discontinuous? Was that? Yeah, I mean at 0, is it defined? No. It is discontinuous at 0. Now you tell me, what kind of discontinuity do I have there? Is it a jump discontinuity? Is it a removable discontinuity? What kind of discontinuity do I have at 0? Well, you have to remember the graph of x squared sine 1 over x, okay? The graph that I gave you before. Anyone remembers the graph? You just have a hole at 0, okay? So it is going to be a removable discontinuity right there. So this was the graph of x squared sine of 1 over x, right? So the limit at 0 exists, right? The limit at 0 is what? The limit of this function at 0 is what? 0, right? The limit of the function at 0 is 0. However, because it's undefined at 0, it's not continuous at 0, right? So I can redefine this function at 0 to be equal to 0 and then make it continuous. Is that making sense? Because the limit at 0 is 0, so redefine the value of the function at 0 to be 0, and then it becomes continuous. Is everybody okay with that? So the limit of this function, x squared sine 1 over x, remember we used the sandwich theorem to show that the limit of the middle guy is 0, right? So the limit of this guy is 0 at 0, but it's undefined at 0, so it has a removable discontinuity. Okay. So removable discontinuity, you should know that the two-sided limits must exist, right, and be equal. The right-hand limit and the left-hand limit, they must exist at that point and they must be the same. And then you can redefine the function at that point by just taking f to be equal to the limit value at that point. Okay, this is a removable discontinuity. G has a removable discontinuity at x equals to 0. Anyone has any questions on this? Not example, sorry. We say that f is continuous from the right at a if one f of a is defined and two the limit as x approaches a from the right of f of a, f of x is equal to f of a. Okay, and you define the continuity from the left in a similar way, right? So what's going to change in the definition? Well, instead of limit going to a from the right, it will be limit going to a from the left, right? And then we will say that it's continuous from the left. So definition of continuity from the left is similar. Okay. Suppose that I have a closed and bounded interval from a to b. So let's let a be less than b. We say that f and let f be defined. Let f be defined on the interval from a to b, right? Okay. We say that f is continuous on AB if f is continuous on the interval from a to b, the open interval from a to b, and f is continuous from the right at a and from the left at b. So if you have a function f which is defined on a closed bounded interval from a to b, we say that the function is continuous on that interval. If it is continuous on the open interval from a to b, and then at a it's continuous from the right, at b it's continuous from the left. Is everybody clear? Let me know if you're done writing it down. You guys are done writing it down? Okay, let's look at some, yeah, go ahead.
What's the, I guess I don't know what that's saying.
Okay, let me, I was going to give you some examples here. So, so let's say I have my x-axis and my y-axis, and let's say I have an interval from a to b, right? Now, if I define a function, I have a function continuous on this interval, means that I have the function is continuous at every point in between a and b. At the end points, right? Maybe the function is not defined outside of this interval, right? So then, what I cannot talk about continuity at a from both sides, right? I have to talk about continuity at a from the right only. Okay, and same way we can only talk about continuity at b from the left. We cannot talk about continuity at b from both sides, right? So maybe if I say, let's say the function is defined this way, at a, that's the value of the function, but at b, let's say the value of the function is given by this dot, right? So then what do I have? I have that the function is continuous at a from the right, but is discontinuous at b from the left, right? So then I wouldn't say that the function is continuous on a to b, okay? Am I making sense? So I will only say that the function is continuous on a to b if the situation is this. Everybody's okay? All right. Here's an example. Let's say I have the function f of x given by x squared minus x minus 2 divided by x minus 2, and I need to determine where this function is discontinuous, okay? So this function is discontinuous at where? Well, I see that the only place where this function is undefined is what? X equals to 2. So we see that f of 2 is undefined. F of 2 is undefined. So f is discontinuous at 2. The question is, are there any other points where f may be discontinuous, right? Well, we have to check whether the limit at any other point is the same as the value of the function at that point, right? So my question then is, what's the limit? Let's let a be a number such that a is not the same as 2. So a is any other real number. A is any other real number which is not equal to 2. Then what's the limit at 2? What's the limit at a for the function f? How do I find the limit of a rational function at a point if that point is in the domain of that rational function? You just plug in, right? That's what we saw when we talked about limits. So the limit is a squared minus a minus 2 divided by a minus 2. However, that's exactly the value of the function at a, right? So we see that the limit of the function at any other point besides 2 is the same as the value of the function at that point. So then there are no other discontinuities, right? So f is continuous on negative infinity up to 2 and then 2 to infinity, right? Besides 2, it's continuous everywhere. So generally speaking, if I have a rational function and to determine where the function is discontinuous, The only possibilities are where the denominator vanishes, right? So basically, a rational function is continuous on its domain, okay? A rational function is continuous on its domain. Am I making sense here?
So what's the point of plugging it in A? Because I didn't
I'm just
solve anything when you put it in.
Yeah, now you don't have to really show this work. I'm telling you. So basically, what I'm trying to make the point is that if I have a rational function, okay, we want to determine where this function is continuous, right?
Okay.
So I'm trying to show that at any given point, the limit is the same as the value of the function. Okay. And so now I'm saying that generally speaking, for a rational function, if you want to determine where the function is discontinuous, all you have to determine where the function is undefined, where the denominator is zero. So, because we know that you can find the limit of a rational function by just plugging in, as long as the denominator doesn't vanish at that point. Okay.
So is there any point where f of x does not equal f of x? I mean,
You mean the limit does not equal f of a?
yeah, I mean,
For a rational function, we are seeing that
like if it's an equation.
I'm going to give you more examples in a few seconds, okay? All right, so that's what we get for this rational. So from now on, if you see a rational function, if I ask you determine where this function is continuous, your answer would be the same as where the function is defined, right? But if I ask you where the function is discontinuous, all you have to determine where the denominator is zero, right? Okay. You guys can remember that? You want me to write that down? Okay. All right. Here's another example. Let's say I have the function g of x equals to the root of x minus 2. Okay. Then this function, we know that the graph of this function looks like what? Let's say here is 2 and the graph looks like this, right? So then we see that this function g is continuous where? G is continuous on 2 to infinity. G is continuous at 2 from the right, right? From the right. From the right only. Everybody's okay? Is that making sense? Because at 2, the left-hand limit does not exist, right? Okay. Here's another example with root functions. Let's say I have the function h of x, which is 1 minus the root of 1 minus x squared. Okay. And in order to determine, first of all, let's determine where this function is defined, right? Where is this function defined? Well, this is defined as long as what? 1 minus x squared is what? Non-negative, right? Well, so then it means that 1 is larger than x squared, right? Which means x squared is less than 1. Okay? Which means x squared is less than 1. Now, what can I say now? If I take the root of both sides, what do I get? I get absolute value of x is less than or equal to 1, right? So what's the domain then? If I have the number line, here is -1, here is +1, then x has to be where? The distance from the origin to x is what? Less than 1? Absolute value of x is less than 1 means the distance of x from 0 is less than 1, so x has to be in between -1 and 1, right? Everybody's okay with that. So the domain is everything in between -1 and 1. Now we also know that, so let's suppose that I pick a number a between -1 and 1, okay? And then if I take the limit as x going to a, okay, of this function h of x, right? We know that if I have a root function and whatever is inside the root, as long as whatever is inside the root has a positive limit, the limit of the root is also the root of that limit of 1 minus x squared. What I mean is that if I'm trying to take the limit of h of x at a, how would I find that? I'll just plug it in, right? So isn't that the same as h of a? Because it's there. So now I can see that this function h is continuous where? H is continuous on -1 to 1. But you have to keep in mind, when I say that it's continuous on -1 to 1, I mean it's continuous at -1 from the left, it's continuous at 1 from the, continuous at -1 from the right, continuous at 1 from the left only, right? So anytime you have a root function, again, what happens is that the function is continuous on the domain. Okay, the function will be continuous on the domain. Does that make sense? So if I give you a root function, if I ask you determine where the function is continuous, you simply say that it's continuous on the domain. So you have to find out what the domain is. Is everybody okay with that? Everybody's okay with that? Here is a theorem. Suppose f and g are continuous at some number a, let c be a constant then number one, f plus or minus g, f times g, they are all continuous at a as well. So what we are saying is that if f and g are separately continuous at a, then f plus or minus g, f times g will also be continuous at a. 2, f divided by g will also be continuous at a. However, given that g of a is not what? 0. Okay, so the ratio of f and g will be continuous at a as long as g of a is not 0. Is everyone okay with that? So let's look at an example using this. Let's say I have the function f of x given by root of x plus root of x plus root of x plus sine x divided by x minus 1. Let's say I have this function. I want to know where this function is continuous, okay? I want to know where this function is continuous. So first of all, let's figure out. The root function root of x is continuous from 0 to infinity. Sine x is continuous where? Sine x, remember the graph of sine x? Is continuous where? Everywhere, right? It's continuous everywhere. The denominator is continuous everywhere, right? So notice that the numerator together is continuous from 0 to infinity only. The numerator is only continuous from 0 to infinity because of the root x, right? Denominator is continuous everywhere, so the ratio will be continuous where? Where will the ratio be continuous, yeah? Except at 1, because at 1 the denominator is 0, right? So this function f is continuous from 0 to 1, and I'm going to put a bracket here, but this function is continuous at 0 from the right only, okay? And then this is from 1 to infinity, okay? Is everybody okay with that? Now whenever you have an end point like 0, right, make sure that you understand I'm not saying f is continuous at 0, I'm saying f is continuous at 0 from the right only. Okay, so that's how I can determine. So what did we use here, right? We used both number 1 and 2, right? In number 1 we are saying that I have root x plus sine x. Both of these functions are continuous from 0 to infinity. So the sum will be continuous from 0 to infinity. And then the denominator is continuous everywhere, but because I'm taking the ratio with the numerator, it could be only continuous from 0 to infinity. But then I have to, number 2 says it's not continuous at 1, right? So I have to exclude 1. Is everybody okay? All right. How about we practice 2 more examples like this. Suppose I have the function g of x, which is given by sine x divided by 2 plus cosine x. Can you tell me where this function is continuous? Can you tell me where this function is continuous? Was that? Why is that? Why do you say it's continuous everywhere? The denominator doesn't vanish anywhere, right? The numerator is continuous everywhere. The denominator separately is continuous everywhere. And the denominator is never 0, right? Because cosine x, the lowest value is -1. It's because you're adding 2 to it, it can never be 0. So g is continuous. G is continuous on negative infinity to positive infinity. Everybody realizes that. It's continuous everywhere. Because the denominator can never be 0, the reason is 2 plus cosine x is always positive, because the lowest value of cosine is -1. Okay, so one thing you want to remember is that polynomial functions, they are continuous on their domains. That means they are continuous everywhere, right? Rational functions, they are continuous on their domain. And root functions, they are continuous on their domain. We saw that. And trig functions, continuous on their domain. And then, well, the inverse trig, exponential, logarithmic function, we're not going to talk about them, but they are also continuous on their domain. You'll see them when you go to calculus 2. Okay? Let me see something here. Okay, so here's a theorem. If f is continuous at b and the limit as x going to a of g of x is equal to b, then the limit as x going to a of the composition of f and g is going to be equal to f of b. Okay. So if the limit of the inside function at a is b, then the limit of the composition f of g of x would be f of b, right? You're basically the limit of what you have inside here, the limit of this guy is b, so the limit of this guy is f of b. The reason you can just say it's f of b because we are saying that f is continuous at b. So the limit of the function f, g of x would be f of b. Here's an example. Suppose that I have the function sine of 1 minus root of x divided by 1 minus x. And then I want to know what's the limit as x going to 1. So what's the limit when x goes to 1? Okay, that's the question. Well, because my sine function is a continuous function, all I have to do is find out where the inside function, here it's a composition, right? What's the outside function? Sine x. What's the inside function? That fraction. So if I find out the limit of the fraction at 1, I can just plug that in for sine and then evaluate sine at that point. Okay. So what's the limit of the fraction? How do I find the limit as x going to 1 of 1 minus root x divided by 1 minus x? How do I find that limit? You can factor out the denominator, you mean? Yes. And another trick would be what? Rationalize. So you get that this is the limit as x going to 1. If I multiply in the numerator, I get 1 minus x. Here I get 1 minus x times 1 plus root x. And then 1 minus x cancels out. I get a 1, and then when I plug in 1, I get what? 1 over 2. So then the limit of the original limit is what? The original limit would be sine of half. Okay, whatever that value is, sine of half. Okay. You have to use your calculator to know what that value is. Okay. You can leave your answer as just sine of half. The value of the limit is sine of half. Is everybody okay with what I said?
Wait, so is there a whole at
for the fraction?
Yeah.
Yeah, for the fraction, remember we are not saying that whether this function is continuous at 1. All I'm doing is computing the limit at 1.
Okay.
So obviously this function is not continuous at 1 because it's undefined at 1. The function is undefined at 1. We are computing the limit, and we are saying, you're right, if I look at this fraction has a whole at 1.
Yeah. So that's just the whole at 1, even with the sign. Even taking the sign of that.
If you take the sign of that, yes, because it's undefined at 1. The whole function is undefined at 1. Okay. So again, we are not asking whether this function is continuous at 1, we are just computing the limit at 1. So if I ask you whether this function is continuous at 1, you'll say that it's not continuous at 1 because it's undefined at 1. Any other questions on this problem? One more fact that I want to give you now is that if G is continuous at the number A and F is continuous at the number B equals to G of A, then the composition function f of g of x is continuous at A. Okay. So the inside function is continuous at A and the outside function is the continuous at G of A, then the composition will be continuous at A. Example, if I look at the function f of x equals to 1 plus cosine x to the half, let's say, and we want to know where this function is continuous, what would you say in this case? Where is this function continuous? Was that? See, 1 plus cosine, so I have even root, right? So if I see, because I have an even root, I cannot have negative numbers, right? But 1 plus cosine x, can this ever be negative? It's always non-negative, right? Because again, cosine x, the lowest value is what? Negative 1. So this value is at least 0, right? Always. So then I could say that, well, it's continuous everywhere. Okay, so 1 plus cosine x is non-negative for all x between negative infinity to positive infinity. So f of x is continuous on negative infinity to positive infinity. Is everybody okay with that? Again, if you think about the function f, capital F is the composition of two functions, right? One of them being the root function, the other one being 1 plus cosine x, right? One of them is the root function, the other one is, so capital F, capital F function here that I have is the composition of f of f and g, where the function f is obviously the root function and the function g of x is 1 plus cosine x. Okay? And what we are saying basically is that the function g is continuous everywhere, and because the value of the function g is always non-negative, the outside function is also continuous on any values of g, right? And so the composition would be continuous everywhere. Is that making sense? Okay. The last theorem is what we call the intermediate value theorem. This will be called the intermediate value theorem. I am going to refer to this as IVT, okay? Later on, I'm just going to say IVT, intermediate value theorem. And what it says is the following. Let f be continuous on the interval from A to B, okay? Let me say it in a different way. Oh, it's gone. Let f be continuous on AB if L is any number between f of A and f of B. So whatever the value f of A is and whatever the value f of B is, the number L is in between the two. So if L is in between the two, then f of C is equal to L for some C in between A and B, okay? So for some C in between A and B. Okay? Okay, so what we are saying is that, let me explain this by using a graph. Let me know if you're done writing it down. Are you guys done writing it down? Let me explain to you what it is saying. Basically, this theorem is telling you the following. Suppose that I have a continuous function from A to B, right? And if you look at the graph of the function from A to B, and if I start with the point A, f of A, I can trace the graph without lifting my pencil, okay? Now, see, let me give you an example here, what this is saying. Let's draw my x-axis here. And my y-axis. Let's say I have the graph of a function which looks like this. Okay. So let's say here is I have B and here is where I have A. Right? So where is f of A? F of A is this point here, right? And what is f of B? Maybe, you know what? Let me use a simpler curve. I think I don't have to be. Let's say I have this following curve. So let's say this is the curve that I have, and then f of B is where? F of B is this guy, right? And then now if I pick any number L, in between f of A and f of B, then there is a number C. There is a number C in between A and B, where the value of the function is L, right? That's what we are saying. So if you have a function f which is continuous on an interval from a to b, and then if L is a number between the value f of a and f of b, then there is a number c for which f of c is the same as L. Is everybody doing okay with that? It's not necessary that f of a is smaller than f of b, right? Maybe the function is decreasing, then f of a would be bigger than f of b, right? So that's why I said L is in between the two. I didn't say L is bigger than f of a, L is less than f of b, okay? Okay, so you can see what you should figure out is what happens when you have a discontinuity, when f is not continuous from a to b. If f has a discontinuity in between a and b, then this fact doesn't work anymore, right? Can you think of an example of a discontinuous function where the conclusion is not true anymore? What's the conclusion? If L is in between a and b, then L is a value of the function, right? L is f of c for some c. Can you think of an example where this wouldn't be true? Well, you have to pick a, if you have a continuous function between a and b, then you are guaranteed that that's true. So you have to pick a discontinuous function, okay? So let's say I pick this function here that looks like the following. Let's say I have the function, here is a f of a, and the function looks like the following. And then the function looks like this. So let's say here is b, here is a. The value of the function at b is f of b right here. Here is f of a. And the function looks like this, okay? So this function is not continuous from a to b, right? Now see, if I pick an L right here, right? There is no c for which, so no c for which f of c is L, right? No c such that f of c is L, right, in this case. So the intermediate value theorem would not work without this condition that f is continuous from a to b. Is everybody doing okay with what I said? Okay. Now, what is so good about this intermediate value theorem? Well, one of the things that we could solve now is some of the questions that we can answer with this intermediate value theorem is that suppose that I have an equation x cubed minus x minus 1. And suppose that I want to, sometimes you cannot find an exact solution of an equation. You just want to know if there is a solution. Now, we can use the intermediate value theorem to show that this equation has a solution, okay? So in order to do that, what you need to do is think about this left-hand side. So whatever the equation you have, put everything on the left and call the left-hand side to be f of x. So denote the left-hand side by f of x. So basically then you want to show that the function f takes on the value 0, right? You want to show that the function takes on the value 0 somewhere. How do I show that? Well, but the function is continuous. You agree with that? F is continuous from negative infinity to infinity. Okay, notice that if I show you that the function f has a positive value and the function f has a negative value, right? Then in between there is a value 0, right? So then f has to take on the value 0 by the intermediate value theorem. So let's see, what is f of, can someone tell me what is f of 0? Negative 1, which is negative. What is, can you give me a value of x for which f would be positive? How about 2? What is f of 2? Is that positive? It's 2 cubed minus 2 minus 1, right? That's positive. Everybody's okay? In fact, instead of 0, if you don't mind, instead of 0, I'm going to put a 1 here, because still it's negative 1, right? Still it's a negative 1. 1 minus 1 minus 1, right? That's negative 1. So what we are saying then, imagine this, that we are saying that at 1 the value of the function is negative 1, and at 2 the value of the function is positive, right? So then the function, the value 0 is in between, right? So the function must take on the value 0 somewhere, right? In between 1 and 2. So by the intermediate value theorem, f of c is equal to 0 for some c between what? The value at 1 is negative, the value at 2 is positive, so c has to be in between 1 and 2, right? So here's 1 and here's 2, right? At 1 the value is negative, at 2 the value is positive, so there's got to be a value c in between 1 and 2 where the value of the function must be 0. Is that making sense? Alright. Yeah. Okay, we want to show that this equation has a solution, so what I'm saying, it's the same as showing that the function f takes on the value 0 somewhere. Well, we are saying that the function is continuous everywhere, and the value of the function at 1 is negative 1. The value of the function at 2 is a positive. So then I know that the graph of the function must cross the x-axis somewhere in between 1 and 2 by the intermediate value theorem. Am I making sense? Remember, the intermediate value theorem says if you have a function which is continuous on an interval between a and b, and then if L is a number between f of a and f of b, then there's got to be a c where f of c is L. If L is in between f of a and f of b, then L has to be a value of the function. So here we are saying that f of 1 is negative, f of 2 is positive, and 0 is in between, right? So f of c must be 0 for some c in between 1 and 2. Is that making sense? So you're going to see some problems in the homework where you have to do that. Now you might say, how do I pick the values where the function is negative and positive? You can pick any value. As long as, so if I ask you to show that a function takes on the value 0 somewhere, you have to find a value. If you have to find a value of x where f is negative, find a value of x where f is positive, any value you want to, and then you know that there is a number c in between where the function will be 0. Am I making sense? All right, so I'm going to end here. You can come back at 11:30 for the exam. Okay.